content, but who knows, right? They are completely exhausted and probably were drunk yesterday and 30 early and all that. So it's my great pleasure to introduce Daphne Koller, who got her undergraduate degrees from Hebrew University in Jerusalem and a PhD at Stanford University, and then she was a postdoc at Berkeley, and now she's back at Stanford and doing a great thing, and is an associate professor of computer science, and you'll see why we love it.
Thank you for having me, and thanks to all of you who got up this morning after what I understand has been a very hard couple weeks, very hard summer, to hear this talk so early in the morning. So I'll be telling you today about some of the work that we've been doing on learning probabilistic models from relational data. And this is joint work with very many people who I will acknowledge throughout the talk. So relational data is all around us, and despite the fact that most of the work on learning has focused on simple table-based learning, it's surprising just how much relational data we encounter in everyday life, starting from, of course, corporate databases, the web, which is probably the single largest relational data set out there, where you have web pages and the entities that they represent related to each other via hyperlinks, social networks, biological data, and I'm not going to read this entire list, and of course an area of interest to all of you, which is text and language, where really it's all about entities and relationships, people, the activities they participate in, the places they go to. It's all about these different entities and how they relate to each other. So relational data is all around us, and an important thing is that relational data is actually quite different from the kinds of ordinary flat feature vectors that the bulk of machine learning work has been devoted to. For one thing, data instances are not independent. For instance, to take an example that I'll be using throughout much of the talk, the topics of web pages that are linked to each other are not independent variables. They're all they're correlated with each other. Pages of similar topics are more likely to be linked. Data instances are also not identically distributed. Among other things, they come from heterogeneous populations, such as papers, authors, and so on. People, and they're all coming from different classes. So it's not you do not have the standard assumption of much of the work in machine learning, which is a set of IID instances. So you might think this is a really bad thing, but what I'd like to try and convince you during the good talk is that this is in fact a good thing. That the fact that you have these correlated instances coming from different populations is a source of power rather than a limitation. And among other things, we can start viewing this data in very interesting ways. So the data is now a network or a graph of related instances, and you can start looking for interesting network patterns, interesting patterns in the graph of instances and their relationships to each other. This kind of relational data sets up new tasks for us as machine learning people, new ways of learning from the data. For instance, I'll tell you a little bit about today collective classification of instances that are related to each other, where you're trying to take an entire picture of a whole set of entities and figure out who they are and how they're related to each other. So both the labeling of the entities and trying to label and understand the relationships between them. A problem that we started working on that I won't tell you about today because it's very premature, is trying to identify groups of similar entities. And I'll mention a little bit about that. And clustering of relational instances again. And I'll talk about some of those problems later in the talk. So the framework that we'll be using to address these new learning problems is the framework of probabilistic models. Probabilistic models are based on two components. There is a space of possibilities, possible worlds that we might consider, and then a probability distribution over the space which gives a number to all of those possibilities so that they all sum to 1. Now, worlds can be very simple, such as the tosses of a coin, or they can be much more complicated. So depending on which kinds of worlds we're considering, you can have very interesting probability spaces. For instance, in the standard feature-based or attribute-based representation of possibilities, the worlds, the elements in the probability space, are the set of possible assignments to a set of state variables. in much of the sequence modeling that, that a lot of you do, whether we're doing speech or language, the probability space are a set of trajectories, whether it's sequences of words or sequences of phonemes. And then in much of what I'll talk about today, in the relational setting, the worlds are much more complicated than we usually consider. They consist of objects, the properties of those objects, and the relationships between those objects. And each world is a set of objects with their properties and their relationships. So a very highly structured notion of probability space. In all of these cases, the number of worlds that we have to consider is huge. In this case, for example, if you have n variables, each of which is binary, the number of worlds is 2 to the n. And all of you know just how many trajectories there are in a parse tree and so on. So that gives rise to the need for probabilistic models that can represent these compound probability distributions in a compact structured way. And that's going to be the main focus of what I'll be talking about. So here's the outline. I'm going to tell you about 2 types of structured probabilistic models, an extension of directed graphical models called relational Bayesian networks, an extension of undirected or log linear models, relational Markov networks. I'll talk about 2 kinds of tasks that you can do with these kinds of models: classification, clustering, actually more than 2, and then uncertainty about relational structure. And then I'll finish off with some speculations about how this all ties into natural language. And the first topic is joint work with Avi Pfeffer, Nir Friedman, and Lisa Gator. So let me start off with a very brief introduction to Bayesian networks. It's a topic that I'm sure some of you are familiar with, but let me review the basics very quickly. A Bayesian network is a compact representation of a probability distribution over a set of attributes or random variables. So here's a toy example that I'll use for the first part of this talk before I get to real data. Here is a set of variables representing, say, the difficulty of a course, the intelligence of a student, the grade of a student in the course, the student's SAT score, and the quality of the recommendation letter that Fred will write you at the end of the summer workshop, as he said at the banquet last night. So these are the variables, and we're going to represent the probability distribution using a qualitative graph structure over those variables, where the directed edges correspond at some intuitive level to direct probabilistic or even direct causal influence. So here we see, for instance, that the grade depends directly on the difficulty of the course and on the intelligence of the student. The letter depends on the grade. This is somebody other than Fred who doesn't know who you are but only remembers what grade you got. So these are the variables. The edges correspond to direct influence. And this graph structure has a formal semantics in terms of independence assumptions about the underlying probability distribution. So for example, among many other assumptions, this represents, this represents the assumption, first time I'm using this pointer, that the letter is independent of, say, the student's intelligence given the grade. So as I said, the professor writing the letter doesn't remember anything about you except looking at the grade when the letter is being written. So it's a conditional independence assumption about this distribution. Now this is the qualitative aspect of the network. The quantitative aspect is this thing that came up a little bit too early, which is a conditional probability distribution that encodes the quantitative dependence of each variable and its direct parents. So for example, here we have that, for instance, if the course is easy and the student's intelligence is not that high, then it's only about 26%, actually 22% likely to get an A. If it's an easy class and the student is bright, then they're very likely to get an A, and so on. So for each of the possible assignments to the variable's direct probabilistic influences, we have a probability distribution over the possible values of the variable. So this quantifies, in some sense, the nature of this dependence of each variable on its parents. And if you take that and you add a quantification to each one of the network variables, you end up with a compact specification of a joint probability distribution over this, over the space of all possible assignments to these variables. And specifically, this is done by what's called the chain rule for Bayesian networks, which says, for instance, that the probability of an easy class, a smart student, a B, And so on is the probability that the class is easy times the probability that the student is smart times the probability that a smart student gets a B in an easy class, and so on. So you can construct the probability of any event in this joint probability space by multiplying in one number from each one of those tables. And this turns out to be a very natural representation for many domains. It's very compact because assuming that nodes depend only depend directly only on a small subset of other nodes, although they can depend indirectly on many nodes, then assuming that this locality holds, the number of parameters is significantly smaller than representing a full joint distribution. So if all of these, just for illustration, are binary, you end up with less than 2 to the k times n parameters as opposed to 2 to the n. And this is a significant reduction in parameters with consequent benefits for both representation by hand and for learning from data. And it turns out that these parameters also correspond to very natural quantities like the probability of a student getting a B in an easy class and so on. So this is a Bayesian network. Now, Bayesian networks have been around for about 15 years, and they're incredibly popular in a variety of both research work and in applications. And the question is, what do I have to say about why do they need to be improved? What is it that they do not give us? So Bayesian networks, in some sense, are a propositional representation. Whereas, as I said in the introduction, the real world has objects that are related to each other. Okay, so what? Well, let's look at this example that we have over here. And, well, we can take this little network and apply it, for instance, to Jane, who took CS 101 and got a grade. Take the same network and apply it to George, who took Geography 101, or to George, who took CS 101. And we can use each of these networks for reasoning about this particular fragment of the situation. But then, if we look at these three networks, we realize, for example, that George is the same George in both of these networks. So this is actually the same random variable. And CS 101 is the same in both of these networks. So again, these are the same random variable. So what's really going on here is much more subtle than thinking about these as three independent networks. For example, if we observe that George got an A in CS 101, that Jane got an A in CS 101, then that's going to make us think that maybe CS 101 is not the most difficult class because, you know, we have some instances of people doing well in it. And that's going to make us have a higher probability that George will get a high grade in CS 101. If we then observe, for instance, that George in fact got a C in this class, that's going to decrease our probability that George is smart, and is going to decrease our probability that he does well in other classes. So what we'd really like to do is we'd like to reason across these different network fragments. So these are not actually independent instances. These are all correlated with each other. So what we'd like to do is we'd like to fit this kind of probabilistic model onto a relational data set, taking into account the fact that these are objects and they're correlated with each other. So what we're going to do is we're going to define a language that allows us to define a probability distribution over a relational schema, if you wish, the set of tables in your relational database. So what we have is in a relational schema is a specification of the types of the objects in the domain. For instance, we have professors, students, courses, and so on. And we have the attributes for each of them. So students have intelligence, professors have teaching ability, and so on. Now we also have relationships between those classes. So professors teach courses, students register in classes. So each registration record is linked to the student who registered and to the course in which they're registered. So together, this gives us a picture of the kinds of entities that happen in our universe and the kinds of relationships that hold between them. Such a schema can be instantiated in infinitely many ways. So here, for example, is a schema for a very, very tiny university where you have 2 faculty, 2 students, 2 courses, and 3 registration records. And you can see that these are the objects and these are the links between them. And then, as we said, each object has the properties or attributes that are associated with it. So the teaching ability for professors, intelligence for the students, and so on. The set of possible worlds, going back to my probability space, are all possible assignments to all of these variables. So if you think about my probability space, I'd like to reason about all possible configurations of this universe. Okay, a relational Bayesian network gives me a way of doing that. So what it does is it takes from its two ancestors, if you will, the relational logic on the one hand and the Bayesian network on the other. It takes a component from each one and puts it together. So here, from the relational logic, it takes a notion of universal quantification. So universal quantifiers allow me to state in one statement a fact that holds for all elements in my universe. What we're going to do here is we're going to adopt that, but the thing that's going to be universally quantified is a probabilistic pattern or template. From the Bayesian network side, we're going to take the notion of locality of probabilistic influence, in that we're going to assume that probabilistic influence holds only locally. Each attribute depends only on a small subset of other attributes. But the interesting thing is that the locality here is going to be defined by the relational structure. That is, the things that one can depend on directly are the things to which you're linked. So let's make this a little bit more concrete. So here's my registration record table, and I'm going to say that the grade of a student in a particular registration depends on the intelligence of that particular student. So notice that this follows the link between the objects. That is, this grade is going to depend on the intelligence of not an arbitrary student, but the student that's linked to this registration record, and similarly the difficulty of the class that's linked. Now you don't have to restrict the, and then just like before, we're going to quantify this dependence with a conditional probability distribution that tells us exactly how the grade depends on these two attributes, and that's going to be exactly the same structure that I had in the standard Bayesian network. Now, I don't have to restrict attention to links that are just one step away. I can, for example, follow chains of links. So I can have the student satisfaction in the course depend on the teaching ability of the professor who teaches the course. So I'm following one link from registration to course, and then another one from course to professor, and the dependence goes along this two-link chain. So this is sort of the template level representation. I'm going to have such a template level representation for each of the tables or classes in my schema. And now, whenever this schema is instantiated to a particular set of entities in my, it's a particular domain, I'm going to have what is essentially a Bayesian network that defines a probability distribution over this probability space. So for example, here we're going to have, as you would expect, that this grade depends on this difficulty and this intelligence. This grade depends on the same difficulty because it's the same course, it's linked to the same course, but on the intelligence of this other student, and this grade depends like this. And all of them have the same parameterization, all adopted from the template. So basically what I've done is I've taken the template on the previous slide and applied it separately to each one of these three variables, which leads to a different dependency model for each of them. Each of them depends on a different set of attributes, but qualitatively they're from the same template. And then the teaching abilities, again, follow the two link chains. Okay. So this is the semantics, and for any set of entities and relationships between them, this defines a joint probability distribution over all possible assignments to all of the attributes of all of the objects in this domain. So what do we gain from having such a compound probability space? Well, it turns out there's a surprising amount. So here's our friend George, and let's try and reason about George. So a priori, we believe that students are pretty smart, so George's prior probability for being smart is about 80%. George took Geography 101 and got an A, so that's great, so our probability that he's smart is even higher. He took CS 101 and got a C. Well, you know, that's just one class. Maybe it was a really hard class, and maybe that's so, you know, the probability that he's smart goes down, but not by a huge amount. It's about 70, 75% now. These are the only two classes that George has taken, and if we reason about George in isolation, this is everything that we can say. But now we remember that this is part of a big university with lots of courses and lots of students, and all of these students took classes and got various grades, so green is A, yellow is B, and red is C. And even just us looking at this, we can see, for example, that everybody who took CS 101 except for George got an A. And furthermore, even this guy over here, who got a C in every other class that he took, got an A in CS 101. So thinking about this, we would conclude that, well, you know, maybe this guy is not necessarily that smart. Maybe CS 101 is not necessarily that hard. And if George got a C in what seems to be a very easy class, maybe he's not that bright. And in fact, if you plug in the model that I showed you on the previous slide and run probabilistic inference on this to figure out the posterior probability of the different variables in this domain, you see that the probability that George is smart has gone down to about 25%. Now, what we've done is we've taken very weak influences, very weak evidence about the performance of other students in other classes. And by putting enough of these different weak indicators together and compiling all that evidence in a well-founded way, we've reached much stronger conclusions than we could have reached by reasoning about entities in isolation. So this is what you get, this is what we call the web of influence, is a way of putting together lots of weak contexts in order to reach stronger conclusions. Now, this is a toy example, but as you'll see, this kind of reasoning gets us a lot of power in real applications as well. So, moving on to the next framework that I'm going to talk about is relational Markov networks, and then I'll get to the applications. And this is joint work with my PhD student Ben Taskar, whose thesis this is, and with Peter Abio. So, having gone through all of the discussion of directed graphical models, Markov networks are an undirected version of a probabilistic model. Let me first justify why this turns out to be a useful thing. So sometimes the kinds of dependencies that we like to represent are simply not directed in nature. They're symmetric, and really trying to impose a directionality on them leads to very funny artifacts. So for example, if we have two web pages that are linked to each other, and we'd like to represent the categories, say the label of this page, this might be a faculty page and this is a student page, we want to represent the correlation between them. Imposing a directionality between one page and the other is an artificial construct. And furthermore, given that hyperlinks are not in essence a directed graph, this is going to lead to cycles, and we cannot have cycles in a directed graphical model while still maintaining a coherent probability distribution. So this immediately leads to difficulties in how you represent the interactions of these symmetric interactions. And you can try and solve this by arbitrarily imposing a direction, say sorting all of the web pages on your site and saying this one's the first and all edges go from it on down, and this one's the second, and except for the first, all of the edges go from it, and so on. But that turns out to lead to very bizarre parameterizations and very unnatural models. So what we're going to do is we're going to define a notion of an undirected model, which again is derived from the propositional case. There is a notion of Markov networks. Some of you might know this as Markov random fields or log linear models. This is represented by an undirected graph over some set of variables. And what we're going to have is, we're going to have compatibility potentials which tell us how happy each configuration, let me just give the example instead of doing a formal definition. So here we have a set of students who all participate in study groups with each other. So these are the variables, and they represent how well the student is doing in the class, whether they're going to get a high grade or a low grade. And this, for instance, is a study group, and we're going to associate a compatibility potential that says, well, the state of the world where all three of these get high grades is a good state, has a higher energy than others. But the state where they all get low grades also has a good compatibility because students who study together often have similar performance in a class. So both of these configurations have higher potential, higher compatibility than configurations where there's disagreement between the performance of the students in the study group. And we're going to have one such potential for each study group. And we're going to then define the joint probability distribution simply by multiplying these potentials together. And that gives us basically a joint distribution, which ultimately has to be normalized to give something that actually sums to 1. So this is a little bit harder to understand than the directed graphical model because these numbers don't have a direct interpretation as a probability of something. You should view them sort of as a happiness factor for the distribution. The higher the number, the higher this group contributes to, the more this group contributes to the overall probability weight of configurations where this event holds. Is this making sense? These models are a little harder to follow than. Okay. So we can again take this notion of a Markov network and make it in the relational and move it to the relational setting. So now we have a notion of universals, and again these are probabilistic patterns, but in this case they hold for groups of objects. And we have the same notion of locality, where the locality follows the link structure. So let's give an example from before. This is my original graphical model where I had the directed influence of grades on intelligence and difficulty. But now I'm going to represent an additional compatibility potential between the grades of students who are in the same study group together. So here we have a study group. We have two students, both of whom are in the same class and participate in the same study group. And I'm going to add this undirected edge, which represents this compatibility potential between the grades of those two students. Again, representing the fact that students who study together in the same group are more likely to get similar grades to each other. So we have A, B, B, and CC, and different weights for other configurations. So once again, this model has semantics by grounding it for any particular universe of discourse. So if we take the same universe that we had before, we now have two additional entities in this domain, these two study groups for these two different classes, and that's going to define two additional compatibility edges that are going to join into my probabilistic model and help define a probability distribution where students who study together tend to have similar grades. Okay, so this is everything that I'm going to say about the foundations of this, and now I'm going to tell you about how to actually learn these models and do interesting things with them. So I'm going to start with a task called collective classification. So collective classification has the following structure. You give me, for example, 2 years worth of students who took classes and got grades and so on. You give me that as training data. And for those 2 years, I have all of the information that I possibly want about the intelligence, the difficulty, and the grades. And based on that, I plug it in, I learn a model, and I get one of these probabilistic models as output. Now come a new year of students. And what I'd like to do is I'd like to take this new data and the model and to do inference in that model to reach conclusions. So for example, given this new batch of students, I might be given only their grades. I want to predict how smart they are based on the grades that they took in much the same way as I did in the case of George a few slides ago. So the key things to understand is that the instances that I'm training on and the instances that I'm classifying are actually networks of related students. So it's not individual students, but the entire set that I want to classify. So how do we do this? So one obvious thing to do is to do what the good old maximum likelihood estimation. So I have, for instance, if my goal is to classify intelligence, I have a bunch of instances with their attributes, say the grades, and I have instances that I'm trying to classify, say, the intelligences. And what I'm going to, and I have this graphical model that I'm learning, and I'm going to do maximum likelihood estimation. So I'm going to try and find a set of parameters for my network. These are the parameters that specify the graphical model, these little probability distributions or compatibility potentials, which maximize the probability of the data that I've seen. This is standard maximum likelihood estimation. I'm assuming some background here that I hope is okay. Please feel free to stop me if any of this is unclear. So this is maximum likelihood estimation, and then having found the set of parameters, I can now go ahead and use it for classification. So if I want to find in my new universe, omega prime, all of the intelligences given all of the grades, and I find the assignment to the intelligences that maximizes this conditional probability of intelligence given grades. So that immediately, looking at this, we see that there is a disparity between this and this. right? Because we're trying to fit the joint distribution, but we really don't care about the joint distribution. We don't care about the joint distribution of grades and intelligence. We really just care about classifying the grades. So, oops, sorry, there is a disparity notation. So what I really want is that. I want to maximize the conditional likelihood of the intelligence given grades. That means that I'm training my model to do a good job with this task, as opposed to just training it to fit the overall data. I'm training it to do a good job with this task. So let's see. So this is what I'm going to do. I'm going to train the model discriminatively in this way. And let's see how well this performs. I took out, by the way, all the details of how the training is actually done, because it's fairly standard applications of things like conjugate gradient and so on, which I'd be happy to talk about afterwards if people are interested. So let's look at how this works. Let's look at the real problem, which is classifying web pages into categories. So here's the web page of Tom Mitchell, who created this set of web pages that we're using as a data set called WebKB. Here's his web page. Here's the WebKB project page. And here's the web page of the student on the project. And you can see that not only are these web pages, there are also interesting hyperlinks between them. And what I'd like to get as output from this, so this is my collective classification task, is to take this set of web pages and extract from it something that says this is a professor, this is a project, this is a student, and they're linked to each other in the following way. So the hyperlinks correspond to these kinds of relationships between them. So this is my goal, is to take this and classify it into something that looks like this. So extracting structured data from unstructured data. So you can do a standard classification thing, which is take each web page, classify it into one of these categories using, say, the words on the page. And you can use, for example, logistic regression, which is simply a discriminatively trained undirected model that looks like this, where you have the category of the page linked to each and every one of the words. If it turns out, if you train this model to maximize the conditional log probability of category given words, you get exact logistic regression, which is something that some of you may have seen. So this is a standard way of doing this kind of classification. You can do a little bit more clever than that by noticing, for instance, that the words on pages that are linked to it also have content. So, for example, if the anchor text of this page says working with Tom Mitchell, you can take those words and add them as features to the page. So you're still classifying each page in isolation, but you've enriched the feature space. You now look not only at the words on the page, but also on words on the anchor link. If you do that and you apply your favorite classifier, you get about an 18% error rate, which is not that bad. This is error rate on test data, of course, using fourfold cross-validation. 18% is not bad, given that there are five different labels that you need to classify into. But now is where we start thinking about the power of context. So let me give you an illustration of context from a very different domain. This is one that I'll return to in a little bit. What do you think this is? Okay. What do you think it is now? It's an R. It was very hard to tell before what it was, but now it's very easy. Why is it so easy? Because we have context. It tells us what this is likely to be. Okay. So how does that come up in web pages? Well, here's a web page. I don't know what it is. It could be a professor, it can be a student, it can be a postdoc. It's very hard to tell. But now, for example, we see that this page points to another page, which we don't know what it is either, but it looks like it might be a faculty page. It has faculty-like words on it. Student pages often point to their faculty advisors. So by noticing that we have some information about this page and a pointer from this to this, it increases the probability this is a student. We now have something that looks like a project page that points to this page, and right next to it points to another page that looks like a student. While neighboring hyperlinks from a page often point to the same kinds of pages. So if we think this is a student, then we think this is more likely to be a student also. So again, we're using context to get better classifications. So, does this work? Well, the answer is yes. So here's my collective classification model. We have variables, remember, for the categories of pages, but now we're going to introduce this correlation between the categories of hyperlinked pages. And this, in fact, is the learned compatibility potentials that we have. And you can see some fairly interesting patterns emerging from this. For instance, students are quite likely to point to faculty. Faculty are less likely to point to students, and even less likely to point to other faculty. So you actually learn these correlations between the categories of linked pages, and by putting all of these different things together and classifying all of the pages collectively, remember, we don't know the class for any one of these web pages, but we're trying to classify them as an ensemble. We end up with a significant reduction in the error rate, going down from 18 to about 13. You can do more interesting things.
Could you explain the problem a little more? How many classes are there? Were they labeled? Or?
Sorry, there are 5 classes: professor, student, course, project, and other. These are the 5 classes that the Tom Mitchell's group originally had for those web pages. For each page, you have the words on the page treated as a bag of words, like that. So we're assuming that they're independent bag of words. You also have the anchor words on the hyperlinks that point into those pages, which we're also treating as features of the page here as well. And then you have the links between the web pages. So that's the data set. And originally, what I showed on a couple of slides ago was classifying each of those pages independently using just its features, which are the words on the page and the words on the anchor links pointing the text. And now what I'm doing is I'm trying to find the most likely joint assignment to all of the web pages simultaneously, knowing the labels for none of them, but the features for all of them.
So chance is about 20%?
I'm sorry?
Chance is about 20%?
Chance would be about 20%, but that's 20% error rate. This is 20% accuracy, and this is error rate. So this is 82% accuracy as opposed to 20% accuracy, which would be chance. Actually, the classes are skewed, so you get slightly better performance. I think if you classify everything as other, you get something like 40-some%.
Just not familiar with the task. So
That's fine. No. Please ask questions. Yes?
Did you find the correlation between the words in the different categories beforehand or afterwards?
It was all trained simultaneously. So we took this model as written, and we did the conditional likelihood estimation using gradient descent to maximize the conditional likelihood of the category given the words. And that trained both the potentials, the compatibility potentials between categories and words and between categories of linked pages.
And you kept the distribution of the different categories. You used the probability that a given page was of a given category.
Well, it was all trained to fit the conditional probability of category given words. So you had the raw data and you maximized and you fit all of the parameters, including the potentials for individual categories, to fit the conditional probability.
You kept it.
Right. Yes, of course. Yes?
So some of your links are directional and some of them are not.
Actually, in this model, they're all undirectional.
So you have a global optimum.
Yes, I have a global optimum, which it's a convex problem, whose global optimum you can find using standard optimization methods. Specifically, we use conjugate gradient, which seems to be one of the better algorithms for fitting these kinds of undirected models. Although recently there's been some newer ones based on Newton methods. They're supposed to be maybe a little better. We haven't tried those yet.
And so you have no hidden variables?
Not here, no.
So
I'll talk a little bit about hidden variables when I get to relational clustering. For the collective classification task throughout the whole thing, I'll assume we have no hidden variables. You can introduce hidden variables into these models. You can continue to train them using conjugate gradient. You lose the convexity properties, so you end up with local maxima, which means you have to do various random restarts and so on. We haven't done that very much. We did it once or twice, but it doesn't figure in any of the experiments that I'll be telling you about. Okay. Good. So this is a very simple way of using a relational structure. Let me show you something else that you can do. Here's a web page of a faculty member. And you can see that it has some fairly clear internal structure. For instance, here's a list of graduate students all next to each other. And here's a list of courses all next to each other. So something you can do is you can parse the page and introduce a notion of section, where each section has a variable that corresponds to the type of section that it is. Okay? Now, this can be a section which is a list of students, or it can be a section which is a list of courses, or it can be a section that corresponds to nothing, in which case this will be none. And then we're making the assumption that if this is a section of a particular kind, then there's a good chance that all of the links outgoing from this section are going to be of the same kind. Again, this is not an assumption that we're imposing on the model. This is something that's learned, but we gave it the structure so that it can learn these kinds of correlations by introducing this variable over here. By all rights, this should have been a hidden variable, but we made it observed by labeling those in the training data. In the test data, they're hidden, of course. So what you end up with here is something that allows us to infer, for example, that if this seems to be a student web page, then this is probably a student section, at which point this will also be more likely to be a student web page, which is one of the patterns that I showed you earlier. And sure enough, if you do that, you end up with yet another significant reduction in error, which is completely uncorrelated with the one that we got from linking of hyperlinked web pages. So in fact, by doing both, you get yet another significant reduction in error relative to either one in isolation, which means that overall we have about a 35% relative reduction in error rate relative to logistic regression, which by the way is comparable in terms of accuracy to, say, support vector machines or any of the other strong classifiers that you might think of applying to this kind of data. Okay. Now, this is sort of work that's hot off the press. The experiments were running earlier this week, so you're getting something that's very recent. Let's go back to our original optimization criterion, which is maximizing the conditional likelihood. Okay. If you look at this, you see that I don't actually care about fitting the entire conditional distribution of target values of labels given the features. I really care about classification, which means I care about the best one. Okay? So what I care about is not the entire distribution of labels. I care about the fact that my target label, Y star, is going to be better than anything else. I don't care about the relative orderings of other labels, for example. So, skipping past all the math, let me just sort of say one thing. It turns out that sorry, my animation got screwed up. This is what happens when you make slides on the airplane to match your very brand new results. The classification that maximizes relative to any kind of log linear model is simply the dot product between your weights and the features that define your domain. This is standard log linear classification. I hope this is, yes?
When you say is that P a multinomial distribution?
No, that P is a log linear. It's a sum, I'm sorry, it's an exponential of the sum of weights times features, normalized. So,
I know what it is.
Okay. Yeah, I just think it might be useful to have it written up because, so it's an exponential of the sum of Wi f of xy normalized. And that means that if you're trying to maximize this, it's the same as maximizing the dot product of w times f.
Why do you use that instead of multinomial distribution?
I'm not sure how you would use a multinomial distribution over this very high-dimensional space.
Well,
I mean, in some sense, it's a definition of
you can make classes of the words, for example. I mean, there are ways, but I see.
It's. Maybe,
No,
I'm not sure what you mean by.
I did something like this with multinomial.
Okay.
I understood
Okay.
why you chose that.
So let's think about what we care about in terms of our optimization criterion. what we want, as I said, is you want the true label to have the highest weight. You want to train your weight so that your classifier is giving you absolutely the right probability, is giving you the right label. So going back to our word example, because it's easier to think about it in web pages, you want that the word, if you want to classify words, you want the most likely word relative to your model to be this, which means you want this word to have the highest weight, higher weight than this word, and all of the other 26 to the 5 minus 1 possible words in the English, non-words, letter sequences in the English language. So you want this to be higher than all of this. So you can view this as an optimization problem. It's a huge optimization problem. But in fact, you can use various tricks based on ideas from graphical models to actually represent this huge problem compactly. And I'm going to skip past this because otherwise I'm not going to finish. And it turns out that by doing that, you end up with significantly improved accuracy. So by moving your optimization criterion one step closer to your actual target task, you end up with a significant reduction in error rate in addition to what we had before. So here we had, remember this is logistic regression. This is as far as we got with maximizing conditional likelihood. And this is when you try and maximize the actual discriminative power of your model. And that gives you, again, a significant reduction in error. And I put that in because I know that many of you are interested in sequences. If you do this for sequences, say for the optical character recognition task that I kept using as an example, then you end up with some even bigger gains in accuracy. So here, for instance, is the accuracy for classifying words by doing each letter in isolation using support vector machines. This is what you get from conditional random fields, which is a discriminatively trained sequence model, a discriminatively trained hidden Markov model. This is what you get from doing something that has both. It's a support vector machine in that it only tries to optimize your classification, the delta between the best sequence and all of the correct label and all of the other labels, but it also captures the correlation between neighboring words. So it captures this context thing, and you get something that's significantly better than either one. Let me skip forward. How am I doing for time?
Well, we know what time it is. It's only 20, but you can have another 15 minutes.
Okay. Let me very quickly talk a little bit just about relational clustering. You know what? Let me skip past this. Actually, you know what? I'll do just the example. Sorry. The new stuff always takes longer than you think. Okay, so here's a different task that we might want to do, which is the task of relational clustering. Here your input is a bunch of relational data which is unlabeled. You have some attributes, for instance, students' grades, but you don't have the labels for those instances. What you actually want is you want to cluster them into groups that are similar relative to each other. So your output here is not just a model, but also a coloring, if you will, of the nodes in the graph into one, in a way that all of the red nodes are similar to each other, all of the green nodes are similar to each other, and all of the blue nodes are similar to each other. So let's think about what that means in the context of a real example. Here's a real movie database. It's the Internet Movie Database, where you have movies, and you have actors that are linked to the movies in which they acted. And if you think about the schema for that database, you have movies. Movies actually have some attributes like the genre and the MPAA rating and so on. Actors have no attributes. And directors have no attributes. Actually, actors have gender, and directors don't even have that, it turns out. So, so what I'd like to do is I'd like to cluster each of these types of entities into coherent clusters. Now, how do I do that? Here's where I can introduce hidden variables. For instance, the type of movie, the type of actor, and the type of director. But I don't know anything about those types. I just know that there's, say, 10 types, which I arbitrarily selected. The only thing I do know is that the type of a movie is correlated with the type of actor who acts in that movie and the type of director who directs that movie. Otherwise, I don't know anything. I take this model and I can train it using the expectation maximization algorithm, which I'm sure most of you have seen before. So I can run EM on this, training it with these hidden variables. And what I get as the output, as I said, is not just a model, which is not that interesting in this case, but also a partition of each type of entity, for instance, each class of entity into a set of subclasses corresponding to the different types. So here's the EM algorithm, which I'm going to skip past because you all know what it is. But here's the types of movies that I ended up with. So here's the movies that fell into class 1, and here's movies that fell into class 2, and then there's other classes down below. And you can see a very natural partition of movies, say, into children's movies and musicals, or into those big blockbuster action movies. So a very natural partition. Now that's nice, but it's not wildly impressive because, as you saw, we have a fair number of attributes for movies, and many standard clustering algorithms will be able to take movies and naturally cluster them into something that looks sort of like this because there's enough attributes to use. What's more interesting is this. Here's the clustering of actors into types, and if you remember, we had no attributes for actors. And nevertheless, just based on their interaction in the relational structure with movies, we ended up partitioning people like Sylvester Stallone and Bruce Willis and Jean-Claude Van Damme and our future governor into one cluster, and people like Anthony Hopkins and Robert De Niro into another cluster. So a very distinct set of very natural clusters of actors. And similarly, we separate out people like Alfred Hitchcock and Stanley Kubrick on the one hand from big blockbuster directors like Steven Spielberg and James Cameron on the other. And again, this is without any attributes, just on their interaction and relational structure. Yes?
You did have to specify the number of
Yes.
types.
We could do some kind of Bayesian model selection or cross-validation over the number of types. We didn't do that in this experiment, but there's obvious methods that you can use to get around that. But it would be the right thing to do. Okay.
So you had movies, and the movies were classified.
The movies were not classified.
Could you put that?
Sure.
That's
The movies had genres.
okay. That's what I mean by being classified.
They aren't. That's not a classification because there are about 15 different genre variables, each of which is binary, and approximately 3 or 4 of them are true for every movie. So you have movies that are classified as comedy and drama and thriller, for example. So it's not actually a. I put it in as one variable because otherwise it would the picture would be too cluttered. But it's actually about 15 different binary variables.
Number of votes means in
IMDb.
In Oscar nominations.
No, this is actually, I think this is number of votes that people in the IMDb database, people get to vote on movies in the IMDb database. And big blockbuster movies often get tens of thousands of votes for how highly it's ranked, and little art theater movies often only get a few hundred. Okay. Okay, let me very quickly talk about additional things that you can do with these kinds of models that I think might be of great interest in terms of language problems. So here we can be uncertain. We can now represent uncertainty. Now we've made objects first-class citizens in the model. we can represent things like uncertainty about which things are linked to each other and what type of links do they have. And we can also, and this is very interesting work by Stuart Russell's group at Berkeley, represent uncertainty about which instances are actually identical, the same as other instances. So let me very briefly just go through this. I don't have time to go into the details, but the basic idea that we have is that we can define a notion of potential links between things. So we can introduce an object for a link. So I'll just do this as an example. So here what we've done is for every 2 pages that have a hyperlink, we've introduced a variable saying, is this a real relationship? And if so, what kind it is. So this is a random variable that characterizes the kind of relationship between those 2 entities. And we've linked it in terms of the compatibility to the category of the pages that it links, thereby allowing us to capture things like if an advising relationship is something that usually happens between a faculty and a student. So even though I don't know that this is a faculty and I don't know that this is a student and I don't know that this is an advising relationship, I'm allowing myself to capture the kinds of patterns that, that hold between them. I also allow myself to introduce compatibility potentials between little triangles of relationships. So for instance, I've introduced for every triangle of links in my data set, I've introduced a compatibility potential that allows me to capture things like students are likely to PA courses taught by their advisors. Okay? So again, this is the kind, this allows us to capture little graph patterns that are more common in the data. Learn how likely they are, and then use that to classify the kinds of links that we actually see in the test data.
Do you presuppose that there are students and courses and stuff? No.
No, I presuppose that there are. I mean, the labels, the kind of labels, are in this case given to me. This is the collective classification task where we're assuming that we know that there's these things called students and we know that there's these things called faculty, but I don't know who's who.
That's right, but you know that there are teaching assistants, and you know they are. And do you know that you know that there is a professor in charge of teaching assistants? Well, I mean,
you can't. This is a question of how rich you make your ontology or your schema. You can put that in which case you will get more informed answers, but you don't have to. So we, for instance, have a notion of teaching assistant and a notion of professor and a notion of advising relationship. And in the training data, those are observed. And then in the test data, we don't observe any of this, and we have to predict all of it simultaneously. Is that?
yeah, well, I'm just wondering whether it sort of finds out from the data that there are these relations between some people and some other people, or whether in fact there is a, I don't know, expectation that there are such, and you only don't know who is who, but and who is in which relation to who, but you know there are such relations.
In this case, the latter. What I'm trying to do here is a pre-supervised task. This is not the clustering task that I was doing before, where you're trying to discover, say, classes of entities in the data. You could also imagine using the same idea to discover classes of relationships in the data. But in this case, I'm doing the supervised task, where I'm assuming that you gave me a data set consisting of, you know, students and faculty and TAs and so on, and you told me in the training set that these are students, these are faculty, this professor is this student's advisor, and so on. I use that for training my model, and then I'm getting a whole new data set where I don't know anything, but I'm trying to classify it into the same set of relationships and class types that I had in my training data. So it's a standard supervised classification task, except that I'm trying to classify links as well as entities. Does that answer?
Yes, yes. Yeah.
So in your training data, every hyperlink has a type label saying it's this type of relationship.
Or none.
Every triangle has.
The triangles don't have labels. Each link has labels. The triangles don't have labels. The triangles are ways for me to capture higher level structures between these types of relationships. And bottom line is, it it works much better than trying to classify links in isolation. So this is the error rate if you try and classify links in isolation, and this is the error rate that you get from trying to classify sort of these much richer models that have, you know, entity types and correlations between entity types and these little triangle patterns, and you get overall about a 73% reduction in error rate over a flat approach. The final thing that I'd like to tell you about is I think something that's very important for the notion of, for questions in language. This is a question of identity uncertainty. This is work by Hannah Passola, who's a student of Stuart Russell at Berkeley. And the question here is, given what we're trying to do is we're trying to figure out which objects are actually the same as which other objects. So we're trying to solve, if you will, the co-reference problem. And in this case, our probabilistic model defines, in fact, a partition of objects into equivalence classes. That these objects are actually, in fact, the same object. Not that they're similar, as in my clustering task, but they're, in fact, the same object. In which case, objects that are in the same equivalence class actually have the same attribute values because they're the same object, so they better have the same attribute values. And they use this for citation matching, which is actually a fairly hard problem because different citations for the same paper often look very, very different. So they came up with a probabilistic model for citations in which names can be corrupted, and you can have sort of different ways of referring to the same author, different ways of referring to the same journal. And this is the model that they had. For example, we have the citation refers to a paper. An author appears in a citation. And for example, the observed title is some distortion of the true title of the paper. And the observed name in a citation is some distortion of the true author's name. So you have some notion of corruption or reformulation of names of both papers and authors. And it turns out that by doing this kind of probabilistic model, you end up with significant improvements in accuracies. This, by the way, is the opposite graph from what I showed you before. This is higher is better as opposed to higher is worse. So this is accuracy relative to the state-of-the-art citation matching system. And it turns out that overall, on the average, you get a 61.5 reduction in error rate relative to the state-of-the-art. So you can use these kinds of probabilistic models for reasoning about what's the same as what. So let me just conclude very briefly with some speculations about why this might be of interest to you, why you might care. And I apologize in advance. This is an outsider's perspective, not somebody who does language research. So this might be very naive, but let me just sort of tell you why. Let me just skip past this. So why should you care? Let's think about a very simple language task, like word sense disambiguation. Here's a sentence. It's not a good sentence?
It's not a good task, it's not an easy task.
Well, it's one of the more basic ones. I didn't say it was easy. But it's certainly one of the starting points that you need for language. So there's two notions, at least, of the word advisor. At least two that are relevant in this setting. At least two senses for gave, two senses for feedback, two senses for draft. So that's an awful lot of different senses for this sentence. Now, neighboring words are what one typically uses to try and do disambiguation. So you look at the neighboring words and you try and figure out, based on those, what is the most likely label for each word. And that works surprisingly well, but it might not be enough. But sometimes you might consider, maybe you can gain more insight, this is a hypothetical, by considering compatibility between senses of related words. Now, related words can be nearby words, but it can also be senses of words that are related to each other that might not be nearby in the traditional sense, like the subject and the verb of the same sentence. Or, more interestingly, the same word that appears earlier in the document as in the single sense per discourse that is so powerful in trying to do disambiguation in many cases. So you can correlate the senses of related words in this kind of model where your objects are the words in the sense. Their attributes are various things like their sense, maybe the gender, the number, and so on. And you have these links between them. And then you have compatibility parameters that you might learn from tag data, or you might be able to use some prior knowledge in order to figure out the correlations that you have between these senses of related words and try and do collective word sense disambiguation instead of trying to label each word in isolation with its most likely sense, as is the most standard solution to this problem. So, let me get past this. A more interesting thing that you might want to do, and I think this is a very challenging and interesting problem, is trying to extract relationships. So here is text, and you might want to extract from this, for instance, this says, Acme's board of directors began a search for a new CEO after the departure of current CEO following allegations of creative accounting practices. You might want to infer from this, for instance, that Jackson is a departing CEO of Acme, and continue from that, getting some more text to consider some other more interesting, some other relationships that happen between this and other entities in this domain. Well, now something that you can try doing from this is trying to put together these relationships as we did in the graph patterns to figure out, for example, that if you had one piece of information saying that Miller was a candidate for this job, and then Miller made an announcement regarding this company that she was likely hired as the person holding this job. So under the assumption that only officials of a company can actually make announcements regarding stock buybacks. That's fairly standard. Now, this kind of relationship is something you might hope to use in order to extract relationships from the text, putting together weak evidence about different relationships in the text in order to get stronger, more interesting conclusions.
Do we know a priori that only offices can commit companies?
That's an excellent question. Ideally, this is something that you would learn from data. So this is a way that you would use a learned model, and trajectory that I hope to convince you is an interesting one to follow is where you would try and learn these models that represent how likely different entities are to participate in certain relationships, in much the same way that we learned that professors are more likely to be advisors than other types of entities, and so on. So you would learn these kinds of correlations between entity types and relation types from data by looking at a whole bunch of examples of text, and then having those, you could then get that, you could hope to reason using that conclusion in a case where this is more ambiguous, such as this. Let me skip past this. And answer your question. Even now, statistical NLP reveals patterns between objects and relationships. So this I got from a very standard corpus of simple verb-noun correlations. And if you see that 24% of the times the teacher occurs, it occurs with the word be. In 3% of the time, you train teachers, you hire teachers, you pay teachers half as often as you hire them, you fire them about the same rate that you pay them, and sometimes you even serenade teachers. But this is purely at the syntactic level. These are correlations between words. But you can imagine them as, but you can see that these are implicit surrogates for what are actually underlying semantic patterns, that teacher objects tend to participate more in certain relationships than in others. So perhaps if we took this pattern and learned it at the semantic level, we can learn what kind of relationships certain objects tend to participate in directly from the data, as in fact we're doing now implicitly even at the syntactic level. So to summarize, there's been two competing approaches in natural language processing that attempt to deal with different desiderata. You want to semantically understand what's going on in the text as an information extraction task. But on the other hand, you want to scale up to very large, to new domains via learning from large corpora. And you have to be able to deal with noise and ambiguity. Natural language processing started out with logical approaches, which really were focused on this semantic understanding part, but didn't come with a learning framework. So they could parse your 8 favorite sentences and that was about it. And couldn't deal very well, were very brittle in terms of dealing with noise and ambiguity. Then the field took a very sharp right turn and went to a very different approach, which is the whole statistical framework, where really there was a lot of focus on scaling up by learning from large corpora and acquiring models automatically as opposed to hand engineering these models for 8 sentences, and are much better dealing with noise and ambiguity. But somewhere along the way, the notion of semantic understanding got lost, and there was a much bigger focus on the syntactic problems, like parsing, for example, which are very important, but are not a direct, don't address this problem right now. And what I hope to convince you is that these are not competing approaches. These are actually complementary approaches. And by having some kind of language that combines both sort of semantic objects and relations between them on the one hand, and statistics and the ability to learn from data on the other, that you might be able to actually have a framework that tackles all, that achieves all 3 of these goals. Now this is very speculative, that's why I call this section speculation, but I think it would be a great problem to work on. Thank you very much. I apologize for running late.
No. Any question?
Yes?
Can you talk a little more about scaling up for probabilistic relation models? I mean, what's the size of the data set you're working on?
Okay, that's a very good question.
170 work corpus, parallel corpus,
Okay.
and the inferences about words.
Wait. We're not doing corpuses.
Right,
so
I'm
just
saying,
right.
to get an idea of the scale.
No, so fine. But I just wanted to say that this is all the natural language stuff has been speculative.
Right.
So
Sure.
we are working. Let's see, on the text data, on the web data. There's usually several. A couple of thousand, 3,000 web pages, something like that. 10,000 links approximately between them. And then the words on each page can be, by the time you add those up, it's a very large number of attributes, but they're observed. We've also done stuff with biological data, which I didn't talk about because I thought it was of less interest in this audience, but there we've done work with 10 to 15,000 genes and several hundred arrays, gene chip microarrays, which gives you a large number of, and then for each of those you have an observation. So you have about 15,000 unobserved variables that you care about and several hundreds of thousands of observed attributes of those. So that's about as large as we've gotten.
And what's the experiment cycle like, and how to learn a model or one of the larger data sets?
In terms of time, or?
Yeah, in terms of time.
It depends on how complex the model is. Runs typically take somewhere between a couple hours and as long as a day for learning one of these models. So it's not instantaneous, but it's within the realms of feasibility. Let me say that there's a lot of engineering here that I didn't talk about in terms of getting this to work. For instance, I completely slid over the question of how you actually do inference with these models. Clearly, exact inference in these graphical models doesn't scale up. So we're doing approximate inference like belief propagation, loopy belief propagation. For those of you who've worked with loopy belief propagation, you know that it's a wonderful tool when it works, but it's very fragile because sometimes it just doesn't converge. And we've had a lot of, it took a lot of work to get it to the point of convergence, and we have our own bag of tricks and so on. So it's not a plug and play thing that you just throw in your model and everything just works beautifully. There's, but that's where some of the more interesting research is that I didn't get a chance to talk about.
So earlier in the talk, you mentioned this really interesting objective function where instead of maximizing conditional likelihood, you were maximizing the best as opposed to the rest. So can you say a little bit, you said there was a trick involved. Can you-
Yeah, that's this is brand new work. What we came up with is a notion of a margin-based classifier for these discriminative probabilistic models. So what you're trying to do is you're trying to maximize the margin between your between the most likely, the true target and all of the all of the ones that are not the true target, which is basically what support vector machines are trying to do. So it's an SVM-like objective function for probabilistic models. Now, for the multi-class SVM, we weren't the first ones to come up with that. There's a paper by Kramer and Singer a year or so ago that when you have like 10 classes, it says you want to maximize the margin between the most likely class, the true class, and all of the other ones. Now, when you try and write down those constraints for things like sequences, you end up with an exponentially large set of constraints that you have to write down. It turns out that you can, and this is going to get a little bit hairy technically, so I'd be happy to take it offline, but let me just give a high-level answer. You can, if you take those constraints and write them down as a quadratic program with an exponentially large set of constraints, which is what you would do if you did the naive thing, and you take the dual of that problem, you can interpret the dual variables as a probability distribution over the joint probability space of all sequences. So you have an exponentially, like before you had an exponentially large number of constraints, you have an exponentially large number of dual variables, one for each of those constraints. It turns out that you can interpret those dual variables as a probability distribution. And then you have an exponentially large probability space, which you can use a graphical model to represent. So in some sense, we're taking this exponentially large probability space of dual variables and viewing it as a probability distribution that can be represented, say, using a Markov model in the case of sequences. And once you do that, you can now apply all sorts of inference tricks from graphical models like Viterbi algorithms and stuff like that in order to optimize this this dualized problem without ever representing the exponentially large probability space explicitly, representing it only implicitly using, in the same way that you would represent a Markov model implicitly using compactly instead of representing the full joint. So hopefully this made a little bit of sense at an intuitive level. I have a whole set of slides on that, and if you'd like, I'd be happy to show you afterwards.
Just a clarification, you said you're trying to maximize the margin.
Mm-hmm.
Is this the difference of the log probability?
Yes, it's the difference of the log probability.
So you're essentially maximizing the likelihood ratio.
You're maximizing the likelihood ratio between the correct label and everything else.
And if you treat everything else as a composite hypothesis and assume that the nearest one dominates, then that's essentially the
No. That doesn't quite work. You can do something like that to do constraint generation, but that doesn't work nearly as well as what we have. What we have is actually a closed form, completely accurate transformation between the exponentially large set of constraints and a polynomial-sized quadratic program. That basically, as I said, once you dualize the quadratic program and you end up with an exponentially large set of variables, you can say, well, these are all of the probabilities. You can view each dual variable as a probability over one of the sequences in your, and then it turns out that for this class of models, the probability you can take this probability distribution just like you can take any probability distribution over a Markov model and represent it in terms of probabilities over nodes and adjacent and pairs of nodes. You can represent any probability distribution over a chain graphical model in this way, and that's what we're doing for the probability distribution defined by the dual variables of this quadratic program. So. I'd be happy to show on any of you who are interested. It's a fairly surprising transformation when you see it for the first time, and I'd be happy to show you maybe after I finish answering the other questions. So.
But we want only one more question. Hamish had his hand up.
It's a very short one. I wonder if you've considered measuring the document classification stuff against some of the test collections that information retrieval people use, or perhaps in a context like TREC. It might make it easier to interpret results. I mean, the results are impressive, but it's hard to see how that relates to a lot of the work that's been done in the past on classification.
Well, Yeah, I mean, the data set that we're working with, the WebKB data set, is one of the benchmarks, not in the TREC community, but in the machine learning community for document classification. So we didn't invent this collection. When you're doing something like the TREC collection, the power that we're getting is from relationships between documents. I mean, we're not giving you a brand new sort of classification algorithm for independent instances. So in the TREC collection, the parts of it that I'm familiar with is just a bunch of independent documents, each of them on some topic. So there's no links between them. There's nothing that we can exploit. There's no traction for us.
There is a web track that started. I'm not sure if it was last year or the year before.
Where the web pages are actually linked to each other. Okay, we would have to take a look at that. So, but we would have to have a data set with that characteristic in order for our algorithm to have any traction.
Was there another question, or are we? Okay, well, thank you very much.